Boa tarde a todos. Já estão aí? Espero que todos tenham conseguido almoçar muito bem, esticar um pouquinho as costas, para a gente continuar agora na segunda parte do workshop, agora da tarde. Então, eu vou apresentar agora o professor Pablo Marquet. Pablo is a professor at the Pontificia Universidade Católica de Chile. He received a bachelor in biology from the Universidad de Concepción and a PhD from the University of New Mexico. Pablo works and is recognized by his contributions in the field of macroecology, theoretical ecology, conservationist, and global change, as well as the scalings of evidence in communities, metapopulation models, and dynamic of landscapes. Thank you, Pablo, for accepting our invitation. It's an honor for us to have you here and learn from you about integrating theories in ecology. Feel free to start whenever you want. You can share your screen in the bottom.
Thank you, Vitor. I'm going to share my screen now then. Thank you to you and all the organizing committee. Let me see.
If you need anything, we'll be here, but mute.
There you go. So, I presume you can see my presentation now?
Yes, we can.
Okay, perfect. So thank you very much. Thank you to Tiago and all the organizing committee for organizing this second workshop on community ecology. I'm really flattered by the invitation. And I want to talk a little bit about the integration of theories in ecology. Notice that I'm not using the word unification of theories in ecology. And I'm not going to elaborate too much on that, but that might be something that we might discuss at the end. So we have been worried or preoccupied by how we can integrate theories in ecology instead of just seeing and unbounded proliferations of different theoretical frameworks to understand ecological systems. So we came about a couple of years ago, actually more than 10 years ago, and have been slowly working on the integration of theories. And we have a group which is called NETI, is the Network for Ecological Theory Integration. And we have got together in different places in Chile and the state, mostly at the Santa Fe Institute, where I am external faculty, and also at the Prague. And in those meetings, we came about with a little manifesto, which is this paper I'm showing here, published in 2014, which is on theory in ecology. And I want to talk a little bit about what we say there, and in order to put this talk in perspective. And I'm going to show you that one of the things we are proposing is the importance of building efficient theories. I'm going to define what is that, and I'm going to say that one of the characteristics of efficient theories is that they are mathematical, that they can be couched into a mathematical framework. And I'm going to give you an example of why this is important in order to advance knowledge of ecological systems by proposing or elaborating on some model for the distribution of abundance of a species. So let's get started and let's define, well, first, what is a theory? Just to give you a little background, in philosophy of science, there is this philosopher have thought about this for a long time, and they distinguish three main types of theories: the syntactical or received view, which actually treats theories of axiomatic calculus. They are much more concerned about how you structure the theory, the words you use, and the logical reconstructions and the logical structure of it, more than to the empirical interpretation. You have to build a kind of a logically consistent syntax to deal with reality. With that view was inspired by logic positivism, the beginning of last century, and actually was pretty much run out of use, and it was replaced, I would say, by the semantic view, espoused pretty much by Frederick Soup. And that's view theories are identified as mapping relationships between phenomena and between models and the world. So the interest here is in the meaning and representation, and they feature pretty big the use of mathematical models as to connect this, or doing this mapping between relations to phenomena. I would say that my view on theories is more aligned with the semantic view than anything else, but I should also say that there is a pragmatic view that is also distinguished in philosophy of science, which is very interesting because this view asks about the internal complexity of theories, and as well about the context over which theories develop. And for example, one question that could be important in this context is, what was the impact that Ronald Fisher's stay at Rob Hampstead's experimental station played in actually affecting the way he actually saw population genetics? Probably a lot, because he, at the same time that Fisher was there, Haldane was there, and they are famous for having huge and very kind of interesting conversations on population genetics and by that time the new synthesis. So those are the three views. I would say that what I'm going to be talking about is more into the semantic view, seeing theories as a collection of models, where mathematical models are very important to increase our understanding of the world. So let's define the theory of, we will be using it here. So we will see a theory as a hierarchical framework that contains some simple ingredients as very basic or clearly formulated postulates based on a minimal set of assumptions that should be very clear from the beginning, and from which you can derive a series of predictions which follow logically from the assumptions you made. And these theories should be inherently deductive. It's not that inductive theories or inductive patterns of empirical statistical regularities are not of use, but they do not constitute theories on themselves. They might be model fitting exercises, but to move from there through a theory, there's kind of some road to be over. So it looked like, if I give this definition of theory, there might not be too many theories in ecology, but on the contrary, if you look at the literature, if you do a kind of a little exercise and you ask, is ecology theory rich? And then you go look at the papers, you can find that this is a survey we have done in ecology, and the papers and there are at least 78 theories, like from life history theory to dynamic energy budget theory, species energy theory, Gaia theory, invasion theory, resource ratio theory, disturbance, and you name it. So, and here's the first confusion, because this is just an illusion. There are not too many theories in ecology. That's the way we define it, because most people actually is confounding models with theory. And that's very different. So in the semantic view of theories, a theory is composed of models, but models on themselves and not theories. So models are usually intended to increase our understanding, or maybe they are devised to solve a particular problem within the domain of a theory, but they are not theory on themselves. So that's the first thing we have to be clear about. And probably we ecologists should be a little bit more careful in using the word theory and reflect a little bit on what is the meaning of that. It's great to have to publish a paper with a new theory, but it's actually is silly to some extent if it's not really something that you are advancing your knowledge. You might be advancing your CV, but not the knowledge of the world. So when you have theories and you have competing theories about some particular phenomena, you might want to decide on which one is better than the other. And here comes the work by Jim Loudon. He's a philosopher of science, at the same time as Thomas Kuhn in California. And he was more concerned not on what happens to paradigm shifts and scientific revolutions, but he was more concerned about normal science, so the space in between. So how theories interact with each other. And he provided very interesting reflections on that. And he said that a good theory is more efficient than its rivals. And the way he defined efficiency is that, in fact, they do more and better explanation and prediction with the same number of free parameters. So a free parameter is something that is a parameter in the theory that you cannot account for first principle for it, but actually it's essential to actually make predictions. So the few of those you have, the better. So he said that evaluation of theory is a comparative matter, and the most important comparison criteria should be efficiency of the theory. So I think that's very important. So what is our strategy in this context for building or developing efficient theories in ecology? And I'm going to give you a series of propositions of how efficient theories could be constructed or recognized. So just trying to be provocative here. So efficient theories should be built as much as possible on first principle. And this is, I think this is the most fundamental one, because you have to build theory on what we know is relatively well kind of empirically and theoretically grounded or well justified. I mean, we have to build theory on what we should call core knowledge. So that is quantitative, law-like postulates about processes underlying a given class of phenomena. Let me give you an example. The Arrhenius equation, which gives you a thermodynamic equation that gives you the role of temperature in affecting chemical reaction and biochemical reactions too, is fundamental to building, is the first principle that helps to build the metabolic ecology. So we know that first principle is true. We might not agree on the precise way we capture it probably in Arrhenius equation, because there are alternatives. But we know that temperature plays a role in affecting metabolic rates. And you can build on that in order to understand processes at the level of cells, at the level of individuals, populations, community, and ecosystems. But that's a clear kind of first principle. Another one is the stochasticity, for example, in neutral theory, or probably also neutrality. So why is this important? Because if you have clear and well-grounded first principles, you can actually try to foster integration between theories, because some theories can predict first principle for other theories and so on. So they can interact. Then efficient theories are usually, but not always, expressed in the language of mathematics. Mathematics is just a language that reduces uncertainty in communicating facts about the world. So we should use it more often, and it's a way of minimizing, I would say, confusion and trying to foster integration. It's not perfect. We know since Gödel's theorems and Gödel's demonstration, I mean, there are some facts in mathematics that cannot be demonstrated within itself. So there is a hole in the system. But notwithstanding that, it's useful and allow us to communicate about the world in an unambiguous way. So I say here that they are usually, but not always, because it is not always possible to develop a mathematical language for a particular concept or a particular phenomena. Probably biological phenomena are particularly difficult to mathematize, but it doesn't mean that we should not provide or try to actually make the effort to actually do it. So then I should say that efficient theories entail as few assumptions and free parameters as possible. This, I think, is essential because theories should yield a compressed description of a system or a phenomenon under study. So we should, a good theory should reduce complexity. This is why you should do when you think about theory compression and formulae that actually allows you to describe a lot of phenomena and a lot of dynamics. So there is one Jorge Luis Borges tale with Boy Casares. It's a very nice tale on cartographers. They say, well, there was a city in Argentina where the cartographers did a map of the city that was the size of the city. And they say, you know, you still can see pieces of it in the pampas floating around the air. And well, that's precisely a very useless map. Or if that were a theory, it's a very useless theory because the theory is as complex as what is trying to describe. So a good map compresses information in a piece of paper of a whole city. And a good theory also compresses information about the complexity of the world. Then a theory does not have to be a precise, faithful description of the phenomena under study. We should also value approximations. I mean, we should not forget that science is a process of cumulative knowledge. So it's everything we do as humans, actually. It's called cumulative cultural evolution. But science in particular is a cumulative process. And we should value approximations. I mean, we are not going to get to the complexity of the world and trying to reduce to some mathematical description of it in instantaneously. I mean, it requires a lot of understanding, a lot of people interacting, and a lot of time sometimes. So most of our theories are approximation because we want to build simple theories, and we don't want to actually start complex. We want to go from simplicity to complexity, no the other way around. Efficient theories in ecology provide a known standard against which to measure natural phenomena. So efficient theories should provide that known standard because we should say, well, this is a theory about this. It's well grounded in first principle. You can mathematicize it. You can make predictions, and you clearly know the assumptions, and sometimes they can provide a very good standards against which you can compare the real world. But the standard is something that actually why it's there. I mean, you know that is the result of the action of the first principle. So you at least know something, and you know that there might be a difference with the standard, and then you have a question to ask: why is this different from this? Because you know the standard. So think probably as Hardy-Weinberg's law, principle it gives you this standard, and in many ways also is a neutral theory as proposed by Steve Hubble a while ago. It gives you that standard. You know the result because you know how it was produced, and you can compare the reality against that standard, and you get information. So Finally, I should say that efficient theories are effective. And by effective, I just provide this quote: effective scientific theories magnify understanding, help supply legitimate explanation, and assist in formulating predictions. So that's what is at stake here. So we want to have efficient theories because they are effective too. They actually allow us to move forward to understanding the world faster and better. So, and this is a big issue now. I mean, we live in a time where environmental disruptions and potential surpassing of tipping points in ecosystems and are threatening well-being in this so-called Anthropocenic era. But we need to actually came about a very strong, deep understanding of how the ecosystem work in order to better preserve them, and we within them, because we are part of it. So it's important to move forward and develop efficient theories. That's what I would say. So just to summarize a little bit, efficient theory then and grounded in first principle, express in mathematical language, explain and predict, and the number of predictions much larger than the free parameters they have. So let me talk about what is in green there, express in mathematical languages. And I will give you an example of why this is important. I'm not a mathematician, by the way, but I work with mathematicians and I learn from them. So let's start very simple with MacArthur and Wilson, 1863. I used to, when I was an undergrad and then a graduate student, I used to look at this equation. It was so easy to understand. But then I remember to read MacArthur and Wilson's book, which was very attractive and fundamental actually. And the book was a little bit complicated. I don't know if you try it, but then you feel that it was full of equations. And beyond this, I mean, underlying the simple relationship between number of species and area in island ecosystems, pretty much, there was this complicated theory. And the complicated theory can be couched or can be actually summarized in this equation here, which has the name 3-4. So this equation says that is following the dynamic of the probability of observing an island with S species. And it's given by all these transitions, you know, from that account for colonization. So suppose you have S-1 species and then you colonize, or that you have the process is at S+1 and then one species go extinct. So those are the many different paths you can get to have S species in a given island. Also, you might already have S and nothing happened, so which is this term here. Okay, so this is a master, what is in the stochastic process, this is a master equation. So notice here that S changed discretely, even though this is a continuous equation in time, the number of species change discretely. And further, it just changed from everything is depending on just the present state of the system, which is called a property of this particular master equation that describe a Markovian process. That's the kind of theory, something that just depends, that doesn't have any memory. No, just depends on the current state, what is going to happen the next one. Okay, and these are the transition probabilities for it. So this is the equation that underlies the theory of island biogeography. And this equation, you can solve it, and you can see which is the probability distribution that actually is called the invariant of this process. Okay, so if you look at this figure here, it's also from the book, it's figure 19. They say this is a particular realization of what he has in mind. So here are the classical rates that we see. You know, we have number of species on the x-axis, and here we have rates on the y-axis. One rate is the extinction rate with the muse, and the other is the colonization rates with the lambda. And you see that they intersect. We usually, when we see this or is reprinted in many textbooks, you just see one little line going down, going precisely down to the number on the x-axis. But actually what this equation is telling you is that it's not just a number, it is a distribution of values. Okay, you have a probability distribution, whose expected value is this. Okay, so what MacArthur said was, in principle, one could solve this equation, they say. For our purpose, it's more useful to find the mean and the variance of the number of the species at time t. So they didn't solve it. Can you believe that? Maybe because the solution is kind of standard for this. This is a typical birth-death process, so it's very easy to solve. And the thing is what you assume about the rates, what are the functional form of the rates. So they say this can be estimated in nature by measuring the mean and variance in number of species of a series of islands of about the same distance and area, and hence of the same lambda and mu. Okay, so you can, he said, you know, you can estimate something about this equation if you assume that islands are all equal and they have similar lambda and mu. So I'm saying this because this is a sort of equivalence that hasn't been really, or neutrality is that hasn't been really kind of reflected too much. That is implied in this equation, which is neutrality about places. He was saying basically that let's assume that all islands are equal and they're all well described by these lambdas and mu's, and then we'll be able to derive something about this distribution. I'm going to elaborate a little bit on that, but before that, remember this equation here, and now I'm going to show you the other equation that underlies this other book on the same series, but probably, let me think, 33 should be 34, 35 years later. This is a monograph in population biology number 32. The other one, this one here, was number 1. That was a big start for this monograph series. Nice resource. So here's the master equation. Now this is for the probability of observing k species with n individuals. Okay, and you have exactly the same structure. You have the probability, if you have n+1, then you have a transition mediated by death. n-1, you have a transition mediated by birth, and you get to n. And also, you might be already at n and nothing happened. So what Hubble says here, he assumed that these birth and death rates are not density dependent, but density independent, so that you have more birth events as you have larger n, as well as you have more death as you have larger n. More individuals, more birth, more individuals, more death. And under these assumptions, he shows that this converges to this, you know, so-called Fisher log series distribution, where the prefactor here is theta. Theta is what is called the biodiversity parameter, or the biodiversity number, which is a function of the speciation rate. Okay, so interesting. So you have the same structure for how species, the probability of finding S species as well as for individuals. So we can look at them here together. So here we have the master equation for the number of species within communities, island. And I rewrote it, so you will see how how similar they are. And here's the master equation for the number of individuals within the species. And here's the little problem where mathematics comes to your, or provides you an insight, because they cannot be true at the same time. You cannot have a master equation with transitions in number of species and at the same time have a species being composed of individuals that are changing in number using this other master equation. The way you see this is, I'm going to explain it, but this because if this is true, this actually will be non-Markovian, violating the very foundation over which you actually derive this. And I'm going to try to explain it to you how it's so. So here are the two again. This is, I rewrote it in a slightly different way. So this is the distribution, the species abundant distribution, or the probability of observing K species with N individual. And now you have the one that McCarthy and Wilson derived. Actually, Hubble explicitly says that he derived this from here, from the insular biography equation. So, and this is the probability of observing K island or communities with S species. So let's call that the species richness distribution. So I've always been kind of surprised that nobody have talked too much about it. The species richness distribution, which is exactly how the number of species changes across communities. In part is because McCarthy and Wilson, they didn't want to explore the solution of the master equation they derive. Although there's Richterdin and Goel, they have a book on the stochastic processes in biology back in the 70s, and they make some examples of how that distribution would look like, and it's a binomial. I can tell you that. So these are the final distributions. Then you have to replace the specific form of these rates in these distributions to actually find out have an explicit formulae for the invariant distribution. So let me explain you then, or try to explain you, or what I meant when I say that they cannot be true at the same time. The thing is this. So this is a birth death. It's a Markovian process that will start. Let's suppose here we have a state on the y-axis, and here we have time. So it starts with S species, okay? What this equation says, it says that it will spend a time at this state, and these times are exponentially distributed with parameter mu plus lambda. Because why nu plus lambda? Because S could increase or could decrease. I'm showing just here one realization where it decreases. And it will decrease with this probability, which is the probability of decreasing. And it will then stay for another time in this state, which is also exponentially distributed. And then it will jump again. And it will jump with this probability now here to S species. And it can jump to S plus 1 and decrease. But the jumping, the times between jumps, the so-called sojourn times or waiting times are exponentially distributed. And why exponentially distributed? Because it's the only distribution of jumps that actually doesn't have a memory on it. That's a technicality, but you will see that as you go in time, the process is jumping. And this is what this is doing here. You have the probabilities of death and colonization and extinction. So species are coming in and out, and this process is moving. And the time the process is spent in each state has this distribution. So now suppose that in addition of having this, you have the process also going in individuals. So it means that this will no longer be Markovian in the sense that this time will not be exponentially distributed, because now you will have a vector associated to each species, a vector of abundances. So you will have, I mean, the community, you will have a number of individuals of species 1, number of individuals of species 2, number of individuals of species 3, and you have all possible combinations of changes in numbers of individuals before eventually this process here will change. And it will have to coincide at this time of the jump that eventually one of the species, actually the abundance went to 0. So it's impossible that both processes are Markovian at the same time and describe the same phenomena. I mean, one is not describing the same phenomena, but they are related to the extent that you know that species are, this level of organization are nested. You have individual nested in species and species nested in communities. So they are related. So, but in this formulation, they cannot be true at the same time. So this is, we elaborated on this we have a chapter in this book just came out, which I recommended to you, which is Unsolved Problems in Ecology by Andrew Dobson, Bob Holt, and David Tillman. And where we say that the problem, the event of finding S species at time t now depends upon a large number of possibility of the abundance vector, which is the number of individuals for each of the species in the community at time t, so that the time between transitions S to S plus minus 1 is no longer exponentially distributed. Meaning that ST might be a function of a macro process, but it's not Markovian itself. So it cannot be true the distribution of abundance and the distribution of richness, or the description that given for the number of species in a community and the number of individuals cannot be true at the same time, at least with this framework. So how you solve this? Well, in this book chapter, we propose some solutions, but I'm going to talk about one that we explore, which is changing the framework completely and going to a different way of describing the phenomena, which is the way mathematicians and people start working with to begin with. And which are the guys where I'm talking about? I'm talking this triad here, Seward Wright, Ronald Fisher, and Andrei Kolmogorov. So why them? Because they were interested in diffusion processes. Actually, Seward Wright and Fisher were working on this so-called differential, partial differential equation for gene frequencies. And pretty much they invented or discovered the diffusion process that Kolmogorov, back in 1930s, wrote a famous paper laying the foundation, the mathematical foundations of how you do this in a rigorous way. So they provide the foundation to understand gene frequencies. And there's this famous model by Seward Wright, which is the infinite islands model, where he has about all the probability of observing gene with a given frequency. So and he came out with this equation, which is called a Betavita distribution, where X is the frequency of a particular allele in a population and depends in a structure of population. Remember that Seward Wright was a fan of a structure population, what we call metapopulations now, where P is the frequency of the allele in the total populations, M is the proportion of migrants between populations, N is the effective population size, and X is the frequency of a given allele, and there's a mutation rate. So given mutation and a particular kind of effective population size, you can derive this is the probability density associated to a gene in this structure metapopulation. So What is different here is that they are not following numbers of genes or number of alleles in a population. They are following actually the frequency. And why do you use diffusion approximation? Because diffusion processes allow you to move from numbers to numbers which are discrete to frequencies which are continuous, and then you use a different kind of mathematical apparatus. So here is the divide between the frequency, the continuous kind of thing, or proportions, and then the numbers. We have been, most of the theory we have developed for ecology is based on numbers. And most of the theory that was developed for population genetics was based on proportions or continuous value foundations. So how you work with the continuous variables using diffusion is complicated, but that's why you have to work with people who actually know how to do it. And I had the fortune of meeting Rolando Rebolledo, who is an expert. He worked a long time in France and is used basically on the process, stochastic process school. And he, back in the 70s, for his dissertation, he developed a method to study diffusion approximations. We applied this to understand the abundant distribution. So now we are going to reframe the question of the master equation. Is no longer a master equation because now we are in the continuous. And you came with all this sort of different and more complicated partial differential equation. So the thing is, here is the thing. When you define a system, this is suppose our meta community. So these are the little kind of lines here that define the community. So you have these arrows across it, which is meaning that this community, meta community, is interacting with something outside of it, the environment, other species that were left out, because at the end of the day, these are, at least in practical terms, defined arbitrarily, or because there is something in the main dynamics of this system that you're not considering, like demographic stochasticity or something else. So if you have this, and suppose that you have birth and death events happening in the populations, and they have this form, like here up in this upper panel to the right, where you have the birth transitions are there is an intrinsic birth plus a term, and then you have the death transition, which you also have a death event plus a term, which is a C. If you have this, what we are doing here is saying, well, birth is what we know about birth plus C, and C is anything else that may affect birth rates that we are not taking into account. And we put that as any of the fluctuations induced in the system from the outside or from something that we haven't included as part of the main dynamics. So when the rates are like this, the process eventually will converge to this equation here, the C. C is pretty much proportion. When you transform the number of individuals divided by the maximum number in the meta community, J, and then you have a proportion. So what we are following here is a proportion. And the process converges to this when the number of individuals tend to be large. So it converges to this equation here. This is a stochastic equation. It has these two components, the drift, which is the dynamic of the main system, and the Brownian here, where you have the pretty much the noise. And look at the noise here, the W. This noise has a prefactor, which gives you how intense is the noise. And this prefactor is a function of C. So the coefficient of the noise is a function of C, so it's anything that is affecting birth and death rates that we haven't accounted for, including density dependent effect. So when this equation, in this form, this equation gives you a diffusion process, which as time tends to infinity, eventually it gives you this process here, which is a Fokker-Planck equation that when time goes to infinity, gives you an invariant distribution. So this stochastic equation at any time satisfies this equation, the Fokker-Planck. So this is what the graph here. So you have the process at any time satisfy this distribution, which in the infinity, when times go to infinity, you can actually try to find it, and you find it that for some particular value of these C's and B and D here, which are like this. Okay, so from this stochastic equation, you go to this Fokker-Planck equation, which as time tends to infinity, it actually arrives to an invariant distribution. And it goes to this distribution, which is the beta distribution too, and arrive there only if the rates have this form. And just gonna tell you that this means that B and D are very kind of a dual. They are linear, meaning that there is no density dependence there, and there is no interaction there. So that's what is assumed. And all the interaction and the non-linearities are here in the C term, who actually describe the coupling between the system and the environment. So under this description, which is to a large extent neutral too, but in the proportions, you find the same distribution, the one that was proposed by Stewart-Wright as a good description for the gene frequencies. So the frequency of genes and the frequency of individuals within the species follow the same beta distribution. And let me show you some fits for different communities. Here we have the Ron-Hapstead Lepidoptera. We have coral reefs and birds and some tropical community. It provides a good fit of the data, as good or better than the neutral theory, at least some of the earliest kind of enaction of it. And more importantly, the parameters have a meaning. And this is the distribution here. And you know that there are these two free parameters, alpha and beta. And alpha is associated to dispersal and beta is associated to speciation. And if you graph for all the communities, we actually have applied this for that paper. You have marine communities, shrublands, tropical forests, and bird communities. You could think that marine communities usually will be with higher alpha because they are more connected than land community, and probably bird communities too. So what you see here is that in fact it is true. There is another yellow color here, which are the butterflies that was studied by Fisher originally. All these communities have high alpha, and some of these tropical communities have a large beta, but not large alpha, as for plants community. So there is a good agreement. And here in the inset, I plot the beta on the y-axis over theta, which is the biodiversity number of neutral theory, and you see that there is a very good significant correlation between both. So we have a theory of for the distribution of abundance, which is the proportional distribution of abundance, works on the continuous value function, which is the proportion of species in a given system, and it is the same equation as the one that provide us an understanding of the frequency of genes in a population. So that provides you a way of integrating theories through mathematics, and the diffusion approximation also doesn't rely on this discrete issue with number of individuals and number of species, and then it is not subject to the same contradiction that we pointed out that exists between the master equation describing atom biogeography of metameter species and the one describing a distribution of abundance. So they has the potential to actually unify both. And I just want to recall some of the people who actually have been claiming for a long time the need to integrate population genetics or genes and individuals, or population genetic and community ecology. The other is Mark Valland, which we'll be talking here at this workshop on Friday, I remember. And he particularly said that the force of maintaining diversity of species and genetic diversity are similar, and that an understanding of community structure will come from considering how this kind of diversity interacts. So he was very kind of keen in trying to integrate genetics with community ecology. So, but what happened with the distribution of richness? Well, let me tell you that we have been working out the theory to understand now the richness distribution, or as we call it, the proportional species richness distribution. And these are bird species, 100 of community of bird species in oceanic islands, and these are mammal species in oceanic islands, and the distribution is well fit, significantly well fit by a beta distribution. So diffusion approximations have the potential to actually help us integrate theory across levels of organization, you know, from eventually genes to eventually the distribution of the abundance of a species to the distribution of richness across community. And they seem to follow a very simple and general birth-death process that can be analyzed through diffusion approximations. So I hope I have conveyed to you the importance of mathematical theory. I'm not saying that any theory have to be mathematical, but when you are able to actually develop that way, there is something very strong in terms of detecting anomalies and in terms of generating theories that can be can show you the integration on the commonalities across different levels of organization, from genes to up to the level of species within communities. So this being said, I just want to thank to my friend Rolando, Mauricio, Octavio, and Simon, and many thanks, obrigado, gracias, Shanktatur, Shaltumai, Jus Pagara, and also the National Agency of Research in Chile. So thank you very much.
Thank you, Pablo. I don't speak as many languages as you, but we are very glad for our talk. We have some questions here sent by the participants. When you are ready, we can start.
Perfect. Shoot.
First one from Ingrid Lima. What are the main challenges for ecological theories applied to nature conservation?
Yeah, well, there are many, I would say. I mean, well, some of them is that we don't have a theory of what are the probably John Hart will say, you know, John of the maximum entropy theory of ecology. We don't really know which are the state variables, and he's trying to do something about that, but we don't really know which are the main things that have to be queuing on. I mean, which are the things that we have to preserve because they are core to a system. We don't know if ecological system or life itself is maximizing something. For example, if there is some, I'm not talking about the information entropy, but maybe there's some other thermodynamic property. Since we don't have that kind of understanding, it's very difficult, I would say, to do effective conservation. Maybe we don't have to just worry too much about conserving species, but about conserving functions and how its functions kind of or traits actually mapping to functions and those mapping to species. We don't have a really good theory about that and how you can build a resilient system. We have a lot of maybe discourses and narratives that make sense, but we may not yet have that theoretical understanding. Somehow, I would say that metabolic theory is making a big kind of providing a lot of insight. But I wonder how we can actually move to traits. Well, Brian Enquist and McGill are making good strides on that. But how we actually understand these more aggregate properties of systems. We are too focused on the species. That's a problem. It's easy for people to understand and to actually promote conservation, but it's not very efficient in order to do the kind of conservation we should, given the pressing environmental problems we are facing. So, but we should go there quick. Thank you.
Wonderful. We have a little bit more questions. Second one is from Vitor Oliveira. Do you think we need to integrate more mathematicians in biology so they can help us to translate the patterns in nature to a formula that we can use?
Definitely. I think we should. And I think we should, I think that the biology of this century is becoming increasingly complex. And we should train more theoretical ecologists. We just not too long ago wrote a little piece for Trends in Ecology and Evolution on the need to train more theoretical ecologists and the need to reform the curricula of biologists to put more quantitative science. Most of my students, most of the time when I teach the ecology class, and some of them, they don't even know or remember what a matrix is, or an eigenvalue on an eigenvector. I mean, I know those are abstract sometimes, but you have to. There are some things that we have to master in order to be able to have a little bit of understanding and being able to talk to people in other disciplines. And together we can actually solve problems much better and in a much robust, I would say, way. We need the mathematics. It's not that it's not kind of an empty kind of word. We need it because it's a language that, as I said, provides an unambiguous description of something, of a phenomena, of whatever. It is not self-consistent, I would say, but as Gödel proved, but it's a great help. We invented for that. So we have to try to, and I would say it's a lot of fun to work and learn from someone in a different disciplines. I work with physicists, I work with mathematicians, and I work also with archaeologists, and I love to actually learn how they see the world and how they struggle to actually bring understanding of it. And most of the time, you can bring a lot of insights. So this is interdisciplinary science, but interdisciplinary science have to be disciplinary. So you have to come from a discipline. You are biologists, you bring to the table something. What is important is that you are willing to talk. And you have some of the skills and minimum language to actually communicate with a mathematician. You know, they know all the other, they can bring all the other tools to the table. The way they demonstrate theorems and make lemmas and all that. But together we are better and we move faster. Thank you.
Wonderful. The next one is from Murilo Dias. How could we, as biologists less familiar with math, start by formulating better theories deeply rooted in maths? What would you recommend to young biologists or ecologists hearing us now?
Well, probably you have to be tenacious. I'm going to tell you, one of the things I love books, as you can see, my library here, but I love to pick them up and sometimes, be surprised by reading something that really compels to me. And one of the things I really loved when I went to do my PhD was that I was able to go into the library. That was in the University of New Mexico in Albuquerque. I was there doing my PhD with Jim Brown. And I went to the library. First, it was cool. Outside was very hot. And it was really great because the temperature was optimum. And then you actually can go to the library itself and pick up the books. And that was something completely different from what I was experiencing, because in Chile, you have, I don't know the other country, but in Chile, you have to go to the library and you write in a paper the book you want, and someone goes and pick it up for you, if it's there. But here you can go inside and move around all the sections, so you can just pick books random and see what they're saying. So I spent a lot of time, a lot of afternoons there, just doing my little exploration, like now I do probably through web pages. And one of the books I picked up was a little monograph by Moto Kimura. And I said, this is the mathematical theory of population genetics. And I said, wow, this is very important. It's looked like this is really kind of a core knowledge, and I have to learn it. That was back in 1990. And 30 years later, I met this guy, Rolando Rebolledo. In the meanwhile, I revisited this theory and tried to understand the Fokker-Planck equation and the flux of probabilities and the stuff. And then by just being tenacious, I remember that now I understand it better. I wasn't illuminated. It's hard work, and you have to be tenacious and eventually go and talk to someone who actually can do this. And maybe you get lucky. It's not always that you find someone who actually is willing to or has the skills to. Mathematicians sometimes are very kind of odd, but there are some who actually love this way of doing this, and I've interacted with a couple of them, and it's great, because you think that you're learning a lot. So tenacious, you have to be tenacious and keep trying.
Wonderful.
Thank you.
The next question is from Vitor Adriano. Do you believe that overcharging ecology theories can be ultimately derived from physical theories, considering that ecological phenomena are nested over physical phenomena in nature?
Right. There are famous kind of discussions about that, the physical envy thing. But at the end of the day, this is what I think. The more we know about the world, the more we realize a couple of things. First, we name things in the world, and in order to study it, we name, for example, disciplines. Okay, we say, well, this kind of phenomena are going to be the realm of this discipline, this kind of phenomena, or this discipline, and this other for this discipline. And particularly the physics and biology, which actually were kind of unified at the beginning, but they were kind of thought of as different disciplines. The problem is that we think they are different. We think that this distinction that we made actually exists there, instead of realizing that there is just one complex phenomena, where what we call the inanimate is essential for the animated or biotic world. This is what I like to understand in ecology, to have to take this diachronic view. It's not a synchronic view of how the system works right now, but how this system have evolved since the beginning of life, which were the first kind of ecological interactions that emerged. We have very good clues about that now because of some experiments. How comes these systems evolve, and which are the basic organization of them? So what we know is that the life originated from the abiotic world. So this biotic, abiotic thing is disappearing. So yes, I think that the physics is going to be fundamental to understand biology. Some theories about the origin and further change in what I like to call adaptive matter. Propose that all these big innovations in the history of life are pretty much or can be understood as phase transitions. It's like the living biomass actually is going through this phase transition, and I like to think that this is it might be well true. It's something that have to be worked out, but there is some fundamental unity in life. And if you look at the last known ancestor, all living material descends from this ancestor. All biomass starting to spread from the beginning, transforming itself, transforming the environment, and following some rules. We know some of the rules. We know we have selection here, but we need to find out more. Which are the other rules that can provide us with insight on the transformation of biomass, adapting different forms and different places, and how they interact. So. Oh, it's so exciting! It's so much to learn. But I completely agree. I think that we will be that biology in general is the physics of this century.
Maybe not calling every other rule as a new theory.
Yep.
We have another question from Gabriel Silva dos Santos. Excellent talk. I'm wondering if it's very hard to provide integrate theories when we have a Babel tower of different meanings for the same words like resilience, stability, density, dependence. Should we first try to provide something like an encyclopedia of terms in ecology before trying to provide integrative theories?
Yeah, that might be one way. But still, you end up with a lot of terms. So even if you define them, probably you will. But there is one way of defining them, which is through mathematics. That's the whole point of it. Mathematics gives you this unambiguous description of what you mean by density dependence or density independence. So it can provide a way forward. I'm not saying that other ways of formalizing or other ways of bringing narrative is wrong, but I say that you can make faster progress if you use this kind of a semantic view of theories where mathematical models are more paramount. But I think that that's where mathematics kind of plays a huge role. But yeah, I mean the question is right on. We have this proliferation of terms. We have these proliferations of theories in ecology. Theory, because they are not really theory, they are just models. It looks like we don't have, we need to organize a house somehow, say, well, this is fundamental, this is fundamental, this is fundamental. We should be able to provide, construct on this fundamental. The same as physicists did when they unified, electromagnetism with other forces. Now they need to unify gravity with the other forces and so on. But they know the forces, they know that they are related, but we don't know these forces yet. Kind of. We know we have the principle of natural selection, we have a stochasticity, we have some other kind of insights, but we have to identify them, the build what we call primary principles or first principles. We have to know the first principles and start building on them. The problem is that our discipline is too young, and the other problem is people want to get famous. So in a young discipline, anyone can come and say, hey, this is my theory, and it has my name, and then I feel like, wow. But I think that we should move to a slow science, and instead of the fast, quick kind of science we're doing, where we are like rabbits. There's a lot of carrots, which means whatever stimuli to actually keep doing this. I understand that the system is completely kind of probably you in Brazil too experience it, that if you want to get a fellowship, if you want to get a job, if you want to get a grant, you need to publish. Yeah, okay, I understand. Everyone has to build a CV, but don't forget that at some point you have to slow down and try to turn to the deep, complex questions that might take years to solve. Okay, you can keep it's like this, the Chinese plates. You remember, you have a plate and you have a stick. You can have several of these little plates, rolling around, but then you have to also concentrate on the big problems. Try to move forward. Yeah, but it's complicated. But we are going there, I think. Thank you.
We are going at baby steps, but we are.
Yeah.
The next question is from Ian Moraes. Do you think the actual misconnection between plant and animal ecology can delay the theory integrating further?
Yeah, completely.
Integration.
I mean, looks at our discipline was heavily influenced by the old naturalist, and the old naturalists, most of them were kind of specialized in a particular kind of a group, and now we have a very kind of taxonomically biased way of understanding the system instead of an holistic way. I would love to have data. There's some on all the different organisms in one hectare, and many replicate system of that to understand the relation between biomass of different kind of organisms, and the distribution of traits in a community, and the different representations of that community that you can make. I think that's essential to move forward to much stronger integration, because we are not dealing with the whole system. We are dealing with pieces, with taxonomic pieces of it. I've been working for a while on something that I call the deconstruction of patterns. Is that you can see a system and you can deconstruct it in many different ways. One is a taxonomic view. You can understand, how many of this kind, but you can also take a trait view, and you can also take a biomass view, and you can also take a food web view, or so there are many ways you can deconstruct the system, and all these so-called views have to be related. So then you will integrate evolution with community ecology, with food web theory, and so on and so forth. So because they are related, but definitely we should do more surveys of organisms in different taxonomic groups within a system. And now, I mean, bacteria and fungi, poof, fundamental, you know. So the challenge is great, but now I think we are getting more and more data. Yeah. So thank you for the question.
You're welcome. Next one is from Sidney Pereira. If science is a process of accumulating knowledge, but according to Thomas Kuhn, science progresses by breaking paradigms in revolutions, do we need more theories? What is your perspective on the future of theoretical ecology?
Well, I think it's true. I mean, knowledge is highly nonlinear. Okay, so and the accumulation of it is also. So eventually, think of a big step. Suppose you are approaching a cliff. You know, you are walking there in little step, little step, little step, little step until you get to the edge, and you just do a little step, and you have a huge consequence. Well, that's a revolution, you know, but it's part of the accumulative process of knowledge acquisition and the way we humans do. So eventually, a little change can have huge consequences. As for me, had this realization that the master equation of the Erlang bibliography is incompatible with the master equation of the distribution of abundance. So that was kind of a very simple for my friends mathematicians said, but you know, this can be true at the same time. It was like, wow, this is amazing. There's a major problem here that have to be solved. So that's one thing. And the other is, I think we will become more and more multidisciplinary in our approaches, not only with the physical sciences, but also with the social sciences. And that is happening, I think, is fundamental. But I'm worried about the proliferation of knowledge and also misinformation sometimes. We live in an era where it's very difficult to disentangle, especially for the youngest generations, which is the core knowledge from all the other stuff, you know. And so the more we know, maybe the little we know somehow, because there's so much. It's like this paradox: too much information eventually can lead you to disinformation because you are not able to process all that in the right way. And if you do a bibliographic kind of research now, it might take you a lot of time. Before it was very easy, but now it's a huge task. But you have to read. My advice: you have to read the fundamentals. I mean, what was built back in the 70s, and go back to the classics. Don't forget the classic, because most of the time they said much more than what is transpired into textbooks. And we are rediscovering the wheel like crazy. And we need to move into more theoretical, but have to be very kind of solid stuff. Otherwise, we will. There's this risk that problems in ecology will not be solved, but they will be just out of fashion, and that's a huge risk, I say, because the same problem comes back and back and back and back and back in a different kind of disguise, but it's the same problem. We don't solve it. They just went out of fashion. So we have to be able to solve problems. And I think that is through theory that we will move a little bit to do that. So thank you for the question.
Wonderful. Next one is from Mariana Ilarzi. Sorry if I mispronounced it. An epistemological question. To what extent biology and ecology is not a particular case of the physical-chemical sciences. Maybe it's time to study it as a great discipline and not to go interdisciplines. There could be integration in the knowledge.
Yeah, well, definitely. As I say before, we tend to believe that all these disciplines exist and that the world respect disciplinary boundaries, but the world, the complexity of the world goes beyond that. So I like to think my ideal will be a world that will be post-disciplinary, meaning beyond disciplines. But the way you do that is a practical way. In some practical way, you have to be trained in one discipline. You cannot wait to be trained in all of them because it's impossible. Don't give you a lifetime to actually do that. So in order to actually do it, you have to pick up from where are you going to go to the post-disciplinary world. And you can pick the biology, but not thinking that your kind of discipline is separate from the others. Understanding that you are going to contribute from one perspective to a problem that is not disciplinary. Disciplines are our invention. You know, the world is not disciplinary. So there is a famous saying I like to repeat, which says, the world has problems, universities departments. You know, problems are inherently inter or post-disciplinary. The same is reality and the functioning of the world. So it's we have to move, and I mean, and there are some sub-disciplines that are dedicated to actually study that kind of interaction. For example, ecological stoichiometry, also metabolic theory is kind of a covering the interaction between the physical and chemical as well and the biological, which, I mean, is part of the same phenomenon. And I would say this phenomenon is life. Not that it's biology, but life is everything. Well, life is why we are here talking about mathematics and the complexity of the world. So, yeah, thank you for your question.
Wonderful. Maybe a couple more.
Yep.
The next one is from Veronica Zepeda. After listening to your definition of what a theory is, I'm curious about what do you think that is the field of study of theoretical ecology, and what do you think that are the main challenges of this discipline?
Right. Well, as I said, I kind of ascribe, I think that we should move forward with kind of a definition of theory which is more into this semantic view. You know, this theories as a collection of models and mappings from models to reality using the language of mathematics. I think that we have to integrate more closely with mathematics as a term of description, as a tool, but then with physics as a way of understanding which are the variables that can be able to describe the complexity of biological systems, and which are the principles that are either, or the variables that are either maximized or minimized. In order to understand how life works, we have natural selection, but it's not enough. There's plenty of more stuff going on. And we want to know if also this autonomous force that we call natural selection actually is minimizing or maximizing something. And we have to come out with theories that are, I would say, integrative, but based on first principles that we agree and we understand which should be the building blocks of theory, and identify which are the big questions. too. I mean, it's not trivial to know which are the big questions. It takes a lot to identify the big questions. So I think physicists have gone much further because they're probably their disciplines and the laws of what they are saying are pretty much easier to be described by the mathematics available. And it's, but we don't have, suppose Einstein in 1905 worked on Brownian motion. He said that this is a fundamental way you can describe how matter moves. Okay, we don't have an equivalent of a Brownian motion for how adaptive matter moves. I would love to know, oh, this is the way, this is core knowledge about adaptive matter. That's the way it changes, it reacts, it transforms. There's some work by some dear friends, mathematicians in France, Sylvie Mellard, Nicolas Champagnat, and some other people working on adaptive dynamics, on trying to understand how biomass is transformed in space and time, and give you this kind of the elementary way it moves, you know. And we are making strides to understand better the world, but still we are very far away from actually reaching real understanding. A big part of the problem is that when we see a paper and it has some equations in it, we get out running, you know. So it is well known that paper will have equations on it. They get much less citations. People don't read them because there is this notion that ecologists like to be in the field and like to marvel themselves with the ecological systems, and that's fine. It's wonderful. And it's great, and there's a lot to be done there. There's a lot of experiments and a lot of documentations. It's like the astrophysicist. You can document a lot of new galaxy, exoplanets, and so on and so forth. You can do the natural history of the universe. But you also need theoretical astronomers, which actually are physicists, to understand what black holes mean and what is the origin of the universe. So the same thing with biology and ecology in particular. We need a lot of natural history to understand what is the complexity of the world, but we need a lot of theory to make sense of it. This is especially true now that we are living into this big data kind of explosion. We need data, definitely, but we also need theory to make sense of the data. Thank you.
Nice. Next question is from Elena Galvanesi. Shouldn't we take a step back and reassess the basic concepts as niche and competition instead of increasing the complexity of models and theories?
I completely agree. We need to step back and see the big picture. And probably in this big picture, what we call competition probably is much more complicated than that. Competition is one kind of interaction that if you put it into the context of other interactions going on at the same time in a system, it can be actually be mutualistic. So there is this famous great experiment that Jim Brown did on the portal experiment on the dipodomys, rodents eating seeds and competing with ants eating seeds too. So there are two kind of dipodomys and two kind of ants, and they interact, compete with each other, and also compete with the ants. And the distribution of the interaction strengths was such that if you remove the rodent, actually the big impact was on the the ant that was supposed to be competing for, because actually what it was doing, it was a mutualistic of this ant, because it was eating the big seeds that outcompete the seeds that the ant like it. So when you take the rodent out, the propagation of interaction actually give you a positive result. So that's the beauty of it. You know, the problem is that we have been analyzing this ecological system first taxonomically, only doing just one deconstruction, which is on taxonomic. We don't have all the taxa, and we don't have all the interactions. And also, we have been doing this in a kind of or trying to understand the world in a pairwise interactions only. You know, so we have to go larger and embrace a little bit of that complexity to actually understand that. And that requires a reflection on what interactions are, why they might be fundamental, or why they're how they interact. And the niche concept, I think, is fundamental, and we have to rethink about it. The niche is, we should do a thermodynamic theory about the niche. I'm not going to say anything else, but that, I think, is a big challenge. That's where physicists and ecologists can do a lot of work.
We actually have another question here. Two, but one is very easy, I swear. First one is from Juliana Macedo Teixeira. Thank you for a great talk, Dr. Marquet.
Marquet, yeah.
Marquet.
Thank you.
Do you believe that functional ecology can be a good tool to test integrative ecology theories incorporating above and below ground world?
Oh, yeah, definitely. That's a wonderful major frontier to understand this kind of interactions. But we are, you know, we are so trapped in language, you know. So we are trapped in language the way we describe the world, below ground. Words like waste, suppose, that their metabolic, the metabolism of bacteria take a resource and generates a waste. It's not the waste, it's a transformation of something that still have free energy that someone else can use. So, but we are trapped on connotation. So it's very useful to think of a world without language. It's difficult too. And then start thinking about it with language. And then you realize that we make emerge a world out of nothing. And somehow we get trapped in our way of describing things. By the way, that's a logocentric critic of postmodern philosophy, and particularly Derrida, and which I really like, because he does the same thing at Gödel does with mathematics, but he does it with our way of understanding the world. And I think we have to step back, definitely, and we have to take challenges like, for example, the plant-soil interactions. But we have to also think of this thing as what if we're taking? It's like, suppose that the roots now are coming out of the soil. I like to think that way too. But it's the same thing, you know. It's like the foliage is immersed in air, but the roots are immersed in soil. So there's some very kind of a similarity. It's only the media that change, and what is going on in the soil, and all the interaction that we are just beginning to understand. And I mean, it's the complexity there is fabulous. It's just, and I really agree with this question. I think that functional ecology has a lot to say and actually move us into a more integrative view, definitely. And there are some people working. There's a lot of people working on this, you know, in different parts. David Wardle and some others. So Peter Reich and Brian Enquist too. And so we are making good good advances. We will eventually have a theory of it, and hopefully it's going to be compatible with the other theories we have. Exactly. Otherwise, it cannot be possible, isn't it? Because it's just one phenomenon.
Right. And the last one is, what books do you recommend for starting? There are some people asking. Or start with mathematical biology and ecology.
Well, in ecology, I really like Ricklett's, you know, book on the economy of nature, because it's very integrative, and you know, in mathematical ecology, there are so many now, but I remember reading, for example, Edelstein-Kechet book, Leah Edelstein-Kechet book, and then there are some books on probability. Someone said to me once, it was this guy who worked at Barrow, Colorado. I don't remember his name right now, but he said to me, the only thing you need to know is probability theory, and know it well. I mean, from the basic probability into stochastic processes. So if you can find a good book on that, there are some books, very interesting ones, but I think a basic book on probability theory would be kind of a good thing. We have some in biology. I mean, Carley and Taylor and so on, but actually this stochastic process in biology by who is that? Goel and Richterdin. Stochastic process in biology is very good because it give you all the theory and examples, and they actually solve the MacArthur-Wilson equation and say something about it too. But that's a very good one too. Yep.
Wonderful. Thank you very much. I would like to thank you, especially in the name of the second workshop of community ecology. We are really glad for your mind-blowing talk.
Thank you.
And we'll invite you to, if you want to continue, to watch the others. And we'll have a break now, and we will turn at 4 p.m. in Brazil.
Thank you, Victor. And all my thanks to you and the rest of the organizing committee and team. Thank you, and thank you all the people who actually was looking at my presentation.